So glad to see everybody's here. Tonight we're going to have a fairly short lecture, and then we're going to look at some review concepts for the test. And anytime we have left, we can spend actually working the review problems. I have 10 review problems. The notes are already posted, so we can work through some of those problems. You can look at them as we go through them and see if there are any of those that you want to work tonight with the time that we have left. So let's start with the do now problem. I have not yet graded your homework 7. It'll get graded, probably tomorrow. And that means if, you couldn't get the mini homework 8 up today, then, you could put it up tomorrow. I'm not going to grade those probably until Friday. So that's good news for you. That's the advantage of an online class, right? You can just upload those that homework that was due at 6 as soon as you can. I probably won't get to it until Friday. But let's go ahead and look at one more proof by cases. This was a due later problem from an earlier day that we met. I think it was a due later problem, maybe from day 13 or 14. I can't exactly remember. And it's a statement about perfect squares. It says, hey, if you've got an integer n, then n squared either looks like 5k, or it looks like 5k plus 1, or it looks like 5k plus 4. And it's an interesting take on perfect squares because it tells us if you divide a perfect square by 5, you're never going to get a remainder of 2 or 3. You can only get a remainder of 0, 1, or 4. And I find that kind of interesting. So just take a few minutes now and write the hypothesis for a proof by cases and include that QR theorem, invoke the QR theorem with D equals, 5, right? Because we're dividing by 5 and looking at remainders, and set up the cases, okay? So take a minute and do that, and then see if you can write what you wish to show. And then we're going to prove that fourth case. By the way, you definitely want to bring a calculator to the test on Monday night. Okay, you're going to want a calculator. I'll try to bring a couple of extras, but you don't need a big old graphing calculator. 4 function is fine. So I'm just going to give you a few minutes to try to work through this. Everybody should be writing. I'm sure you've all figured out by now that math is not a spectator sport. Hi, Kaja. Hey, Nick. Hey, Danny. Glad to see you made it. Zane, yeah, we already said hi to Zane. Okay, great. Fantastic. Fantastic. Looking good. Okay. So I hope for your proof that you say something along the lines of assume n is an integer or assume n is in z. Then we just say, hey, by the QR theorem, equal 5, n is equal to 5q, or n is equal to 5q plus 1, or n is equal to 5q plus 2, or n is equal to 5q plus 3, or n is equal to 5q plus 4. And of course, q is an integer, right? And our wish is right here, this big, long compound disjunction. So I hope everybody's gotten yourself set up something like this, okay? And, when I grade your homework, I'll see how you set those up. Listen, had a couple of students slip up a little bit and try to use AI to help set up cases. Be wary about that, folks, because it's a real obvious tell. Because we do it for deep understanding. Okay, so I hope you haven't fallen into that. So which is the fourth case, folks? We have 5 cases. Which is the fourth one?
5q plus 3.
Yeah, case 1, case 2, case 3. Here's our case 4 right there. So let's just suppose that that's what n looks like. And I'm not going to rewrite the wish because it's so lengthy, but it's the same wish in every case. We're going to square this baby and see what it looks like, right? So let's just take a look. So n squared is, what'd you get when you squared this, folks? Edwin does a lot of the heavy lifting in the class for everybody, I've noticed, and I really appreciate your participation. Anybody else willing to
25k
pipe in?
25k squared plus 30k plus 9.
Thank you. Perfect. 25k squared plus 30. I'm using q, but you can use k, it doesn't matter. And then plus 9, right? Good. Your kung fu is strong. Your algebra is strong. And we want to break this down because we want to figure out what it looks like when it's divided by 5. So what do we have to do with this remainder? Because what's wrong with 9, as a remainder when we're dividing by 5, folks?
It's not an integer.
9 is not an integer.
If you divide 9 by 5, it wouldn't be an integer.
Exactly. If we divide 9 by 5, it sure isn't an integer. Now, that's a true statement, and I want to, support you that that is a true statement. But any remainder, except for 0, when you divide it by the divisor, won't be an integer. There's something else wrong with 9, though, as a remainder. Remember what we're dividing by. What are we dividing by?
Doesn't have a factor of 5.
Yeah, it's got a factor of 5. It's too big to be a remainder when we're dividing by 5, right? Because the only remainders we're allowed are 0, 1, 2, 3, and 4. So we just have to apply the QR theorem to 9 and break it down so that we can see how many copies of 5 we can pull out of there. And again, I'm so sorry I did not get your homework graded by class tonight because if you'd had a chance to read comments, that might make more sense. But do you see what I mean? Like we can pull a 5 out of there. And 4 now is a good remainder, mod 5, when we're dividing by 5. So we pull out a 5. And let's see, which one of these 3 possibilities do we actually wind up getting when we factor 5 out of everything we can factor a 5 out of, and then we see this remainder. What did we just find out about n squared?
Equal to 5k plus 4.
Exactly. Nice. Right? And isn't that interesting? We started with n equals 5q plus 3, but when we square it, because we got the 9, the n squared actually has a remainder of 4. So don't confuse your wish with setting up the cases, okay? Even though, the wish doesn't include a possibility of getting a remainder of 2 or 3, that wish is a statement about n squared. It's not a statement about n, okay? We have to look at all the 5 different possible ways that n can be expressed. So there will be 5 cases, but if you go ahead and you work the other 4 cases, in each of those 4 cases, you'll either get that n squared looks like this. I think that happens in the first case, right? It's just like 25q squared, so it turns out to look like 5 times an integer. Or you'll get this. I think that happens when n equals 5q plus 1, and I think it also happens when n equals 5q plus 4. Or you'll get this for n squared. That happens when n equals 5q plus 2 or 5q plus 3. See what I mean? So now we'll just go ahead and let's finish this. Let's talk about why that's an integer. So since q is in z, or whatever letter you used for your setting up your cases, and z is closed under, let's see, adding and multiplying. So under addition, you can abbreviate addition if you want on the test, just to, save yourself time. And multiplication, I'll call it k now, is equal to 5q squared plus 6q plus 1 is certainly nz. So, in fact, n squared does equal 5k plus 4. So that wish that either n squared equals 5k or n squared equals 5k plus 1, or n squared equals 5k plus 4, right? We wanted, this big or statement to be true. Well, it is, because we got the component that n squared equals 5k plus 4. That statement that we wish to prove is true. Okay? Questions? So listen, fear not. There's no way I'll ever give you 5 cases, right, on a test. But I might give you a statement that would require a slew of cases and just ask you to set the cases up like this and then work a case or two. That would be fair, right? But I would never give you a proof with more than, 2 or 3 cases on a test. Okay. So again, we're going to have some practice time later tonight where we're going to work on some problems. This is the only part of section 5.1 that's going to be on test 2. I just wanted you to kind of get a little break from proofwriting. We're going to play some games. These are kind of like little puzzles, and you're going to get to learn some new notation. Summation and product notation. Very useful notation. And this is going to set us up to talk about sequences next Wednesday. So next Wednesday, we're going to do sequences and factorial and combinations in choose R. And then starting the week after that, we get to play mathematical induction games. I hope you're excited for that. Ever heard of proof by mathematical induction? Oh, it's a great, powerful tool. Okay, so let me just give you it's not like a full-fledged definition, but I didn't want the definition to get so bogged down in notation that it was just a horror to read. So let me just give you kind of a simple notation about a summation of terms. Now, what do I mean? Okay, we're going to call these terms A1, and we're adding them because it's a sum. So plus A2 plus, keep on going, up to say A sub n. Now, when it's written out like this with the plus signs in between the terms, this is called expanded notation or extended notation. I like to call it expanded form. I think in WebAssign, they call it extended form, but you get the drift, okay? It's all stretched out. But that can be expressed using the summation symbol. Now, everybody in here has seen folks wear their Greek lettered sweatshirts and whatnot, right? Anybody know what the letter for S is in Greek?
Sigma.
Exactly. And the capital sigma looks like this. I know everybody in this room has seen that, right? So that this means sum. Now listen, we can use any indexing variable that we want, and tonight we'll practice with several different variables, but I'm going to just put the definition with K. So K is our indexing variable, and it tells us what's going on with these numbers. It starts with 1 because the first term is indexed with the number 1. So 1 is called the lower limit of the sum. And if you've taken calculus, you've heard of limits. Okay. And then what is the last indexing number that you see in this expanded form? What's the highest number, apparently?
10.
Yeah. So the n will go up top. And this is called the upper limit of the sum. And then what sits right here in front of, well, maybe behind, because we read left to right. But anyway, what sits right here is the term, and we'll just call it a sub k. Now, folks, you've done a little programming, right? Everybody's done a little bit of programming. So you've done loops where you had like some kind of indexing variable like an I maybe or an N that would increment by 1. You know, every time you go through the loop, the I gets incremented plus 1 more. So we start at K equals 1 plus, then K goes to 2. That's our A sub 2 plus, then K would be 3. So the A sub 3 would be here if we wrote it. Keep on going, and it ends up at A sub N, okay? So the A sub k, folks, is actually called the term. I think you gathered that, but I'll just write it there. And by the way, this now is called closed form. I think WebAssign also uses that. That's standard. And the interesting thing is this number up top, it cannot be smaller than the lower limit. The upper limit can't be smaller because this, K is going to start getting bigger and bigger one by one, right? So N has to be greater than or equal to 1. But it actually could equal 1. The lower limit and the upper limit could be the same. And that just means we're looking at a single term that is indexed with whatever that number is. Let's look at an example. And now we get to play the game. And the game is fun where we kind of try, it's like a guessing game. All right, so write the sum in closed form. Use any indexing variable you wish. So here's the sum. 2 plus 5 plus 8 plus 11 plus 14, and I'll stop it there. But have I shown you enough that you see the pattern? So Danny, I see you shaking your head. Yes, cool. So what would be like the next term? If we were going to put another term in that sum, what would the next one be?
17.
How do you know that?
Every number increases by 3.
Yes, we're adding 3 to get the next term. Okay, very nice. Very nice. Okay, so listen, when we write this solution, and I know that I think that the red is kind of hard to see when we're actually live, even though the notes are in red, I'm going to do it in green. I've made that decision. I want to kind of show you how we're going to get a handle on a way to express the general term a sub k. So if we look at 2, that's the first term. We can't say much about it, okay? So we'll come back to that. Sometimes we have to look several terms down the line before we start seeing something happen. But 5, as you noticed, was 2 plus 3, right? We added a 3 to the 2 to get the 5, right? Well, 8 is 2 plus 3 plus another copy of 3. So 8 is 2 plus, it was, 6, right? So this is the game we're playing, folks, in case you wonder why I'm doing this. I'm trying to write enough out that I can see a pattern so that we can express the general term. And we're looking to see what's changing. 11 is 2 plus 9, right? But that's 2 plus 3 times 3. So we're starting to see some stuff is staying the same. The 2 is staying the same, right? This factor of 3 is staying the same, but what's changing is how many copies of the 3 are getting added to the 2, right? And 14 is 2 plus 3 times 4. I think we're starting to see enough here. Now if we kind of back up, what would we put here as the multiplier times the 3 to fill this out for 5?
0? Or
For
1, sorry.
Yeah,
For
no,
1,
you're
it would
good
be
though.
0.
1, but I think you're also now thinking about what we would put here to expand out the 2, right? And that would be the 0. Everybody seeing that? So again, I'm just going to write it one more time, but I am going to use a little bit of color. This is 2 plus 3 times, okay, I'm going to try red, 0, right? So I'm just trying to get my head around what's changing and what's staying the same. Because the indexing variable, whatever we use, whether it's K or J or whatever, it's going to represent that changing quantity. And see how the incrementing is going by 1, like first it was 0, then it was 1, then it was 2, and then it's going to become 3, and then it's going to become 4. Everybody see how that's happening? So this changing value is getting incremented by 1. Let me just make a couple of notes here. The changing value, that's what we're trying to do, folks. We're trying to see what's changing because that's what's going to get addressed with the variable. Gets incremented by +1. And that's always the game. It's always an increment of +1, okay? So now we're going to try to find the general term. In other words, folks, we're looking for an expression. We're going to try to relate the indexing variable to the quantity that is changing in the term expressions. See it? So so we're trying to find what a sub k looks like. Does that make sense? So what would be a good expression for a sub k then? See, we can kind of see it here.
2 plus 3k?
Yes, 2 plus 3, and then what's changing is that multiplier times the 3, which tells us how many times 3 has been added to 2. Does that make sense, everybody? So this is fun. And, it's just like a little puzzle. It's a kind of a nice break. So our answer now, well, let's be sure and read the question. Write the sum in closed form. Okay, we want to write it using summation notation in closed form. So we've got the hard part of the work done. We know what the a sub k looks like. All we got to do now is realize that we need a sum. No, that's not a very nice sigma, but a sigma. And k is our indexing variable. We've decided to use k. We could have used j. We could have used, I. Doesn't matter. And we're going to have to figure out the lower limit and the upper limit. So we just look, just look and see what values k took on. So what would be our lower limit?
K equals 0.
Yeah. K started at 0. Fantastic. And then what is going to be our upper limit? Because we went up to 14. We showed them all.
4.
Good. It's good. And then we write the a sub k expression right here. Parentheses are required, okay? Parentheses are required. And I can explain to you why if it's not exactly clear. It's a thing. If we didn't have the parentheses, then only the 2 would be getting summed up. And in fact, there is no k in that. So it would just be 2 plus 2 plus 2 plus 2 plus 2, 5 times. And then the plus 3k would just be hanging off the end, and it wouldn't even get to change because it wasn't involved in the sum. See what I mean? So we do use parentheses. And that's the answer. Any questions? Want to do another one? The correct answer is yes, but I hear you. It's been a long day. That's funny. I'm looking at some facial expressions. You're cracking me up. Okay. Example 2. Let's do another one, and then we'll switch to product notation. No, actually, let's do something a little different. Here, evaluate this summation. All right, so let's just make sure you understand what that kind of question means. It's the sum, I'm going to use I, from I equals 0 to 3 of 2 raised to the I. So evaluate the sum simply means figure out, what value it has. So it is helpful when you're doing this to write in expanded form, and it's good practice too. There's some there are, I think, 10 WebAssign problems that I've chosen from 5.1 for you to work on between now and Monday night at 6. You get till Monday night at 6. And a couple of them are, write it in expanded form. So, and there are a couple of them that say evaluate, so we'll do both. So this sum from I equals 0 to 3 of 2 to the I is, well, so what would the first term look like, folks?
2 to the 0.
Yeah. Now, this is the part that we have to remember. This is a sum as opposed to a product. We're going to see both tonight. Since it's a sum, we put a plus. Now, the I increments. So what's the next term going to be?
2 to the first.
Exactly. Keep going. Let's go ahead and do it.
2 squared.
2 to the power 2.
Yes, good. And what's that last term?
2 to the power 3.
Nicely done. Great. Fantastic. So this is what we call expanded form. And basically, unless you're some kind of a mathematical whiz, and I know there are those of you in this room, I'm not one of them, okay? You're going to want to write this out like this, So this turns out to be what? Oh, does everybody know? I wanted to ask. 2 to the 0. What is 2 to the 0?
2.
Okay, I'm so glad I asked. All right, anything raised to the 0 is 1. Yeah.
Okay.
Oh, except x equals 0. 0 to the 0 is an indeterminate form. It only arises when we're calculating limits. Yeah, so 2 to the 0 is 1. And that's real important to know that, okay? Plus, of course, 2 to the 1 is 2. 2 squared is 4, and 2 cubed is 8. So what is our answer?
15.
Yep. So that's good practice going the other way. Any questions? All right, here's one that's a little bit different. Write using summation notation in closed form. Two plus 2 squared times 3 plus 2 cubed times 3 squared plus 2 to the 4th times 3 cubed plus 2 to the 5th times 3 to the 4th. Can you see that okay? Here, I'll put this down a little closer so it looks a little bit bigger. So let's find an expression for the general term. So when we look at this first term, again, it's kind of like it was in the first example. There's not a lot going on with that. We'll come back to it. Right? Like once we figure out what's really going on, we can come back. But 2 squared times 3, now suddenly, I'm looking at exponents. I'm saying, oh, there's an exponent thing. And we see what's changing is the exponents, right? Let's look at the next term. 2 cubed times 3 squared. 2 to the 4th times 3 cubed. 2 to the 5th times 3 to the 4th. So what would be the exponent on the 3 in this second term, even though we don't usually write it?
1.
Yeah, there's actually a 1 here, even though we don't usually write it. But we want them all to kind of look the same, right? Because we want this general term to work for every single one of these. So what could we do to the 2 to make it look like these other ones?
3 raised to the power 0.
Exactly. 2 is 2 times 1, right? 1 equals 3 to the 0. 2 times 1 is 2, and it's 2 times 3 to the 0. Exactly. Nice. So what I'd like to show you now is there are several different ways to answer this, okay? Because nobody's told us where the indexing lower limit should be. Like our indexing lower limit was 0 in the last example. Okay. But it doesn't have to be, but it can be. Just depends upon how we want to do it. So we'll do 2 solutions. It's nice to have some choices. And by the way, you've done enough programming to know this. You may not want to be initializing variables at 0. That can cause problems, right? And in fact, sometimes you'll be given something where it is initialized at 0 and you're going to want to do a change of variable. So let's try 2 different ways. But let's try starting at j equals 0. Let's see what that looks like. So we're going to figure out what the general term is, because it really depends upon how we start the indexing. See what I mean? But if we're starting the indexing at j equals 0, nothing deep is going on here with the fact that I'm using a different variable. I just want what would be the upper limit?
4.
Yeah, because the 0, I'm seeing the 0 as the exponent of the 3, right? Does everybody see that? So we need 2 raised to a power times 3 apparently raised to the power j, because we picked j equals 0, right? So what would be the right power expression to go on the 2?
J plus 1.
Careful. Did you say j plus 1?
Yeah.
Is it j plus 1? Oh, it is. Careful, Dr. Good, be careful. That's exactly right. Huh, I was thinking it was j minus 1. Yeah, that's right. Yeah, the power on the 2 is 1 more than the power on the 3. Thank you. Now let's try and start at k equals 1. Let's do a change of variable. Let's say we don't want to initialize the system at 0. Okay, so if we're going to use k equals 1, what would be the upper limit?
5?
Uh-huh, because, we're up in from 0 to 1, we're going to have to up 4 to 5. Also, we can just realize now we're looking at the exponents on the 2, and it goes from 1 to 5. So there's a couple ways to attack that. So what would be the exponent for the power of that would go on 2? What's the exponent for 2?
K.
Okay, yeah. And then what's the correct exponent
K
for the
minus
3?
1.
Yes. Nicely done. Questions? Okay. So good. We played some summation games. Does everybody kind of get the drift here? And this is real important, actually. Sums are actually quite important. When we start proving things using mathematical induction, we're going to be proving statements involving sums. Did somebody still need to see that? I can keep it up here. Maybe I took it away too soon. So let's look at the definition of the product notation. And again, I'm simplifying it. A product of terms. So now these terms are getting multiplied. I'm going to start with indexing at 0. A sub 0 times a sub 1 times dot 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 times a sub n. And again, this is called expanded form because we're seeing all the factors expanded out. Can be expressed using the product symbol. What symbol do you think that we'll use for product? We used the Greek sigma for sum because that's S. What Greek letter is the Greek letter for P? Anybody know? You'll know it when you see it. It's pi. Pi, this is the capital pi, right? The lowercase pi looks like this, right? But this is the capital pi for product. Make it a little bit longer. And then this would be, if we use k as our indexing variable, k is starting at 0 in this sort of example definition, and we're going up to an upper limit n, and this is of the term a sub k. And this, of course, is closed form. Okay, so let's play the game. It's very similar, where we have to figure out a general term. Write this product in closed form. And of course, you can use any indexing variable that you wish. 1 times 5 times 5 squared times 5 cubed times 5 to the 4th times 5 to the 5th times 5 to the 6th. So, I mean, we don't really have to do a whole lot of work at this stage because I think you're starting to see what's going on. But, 1 is the first factor, 5 is the next factor, but we realize right away that's 5 to the 1. And we know that 1 is 5 to the 0, right? So, you just see what I mean? So what's the general term going to look like?
AK equals 5K?
5 to the K, yeah. Because when we say 5K, that means 5 times K, but I think you meant 5 to the K, right?
Yeah.
I'm sure you did. All right, so now we can just go ahead and write our answer because it's that simple. This is a super simple one. It's the product. What's our lower limit for K?
0.
What's our upper limit? Good.
6.
Yep. And then we write 5 to the K. And we don't need parentheses here because it's, just a single term. It's not a binomial. All right, let's do another one. Let's practice some exponent games. Write in closed form. Again. Now, what I haven't got prepared for you is the other way around. The other way around, I'll tell you the mistake that you'll make. If I give you a product like in closed form like this, the mistake that you'll make, and I'm just kind of warning you, is you'll accidentally put pluses in between, right? So you just got to pay attention. If it's the product symbol, you put, the time symbol in between the terms. All right. You'll see some of those on WebAssign, but let's just do one more, and then we're going to do some review. We're going to do a couple different solutions because there are a couple different ways, to deal with this fact that it's 1 over, a number that's getting raised to a power. Does anybody want to take a stab at what the general term would look like? Let's use J. Anybody want to take a stab at what a sub J would look like?
1 over 3 to the power of j.
Exactly. But so we'll call this solution 1. But there's another way to deal with this, right? When the non-trivial part of the quotient is on the bottom. What would be another way to write this? We can still use J.
3 to the negative j.
Exactly. 3 to the negative J. So it doesn't matter which one you use. It'll be fine either way. And so then, our final answer, of course, is going to use product notation, right? So if we use the 1/3 to the J, what's our lower limit and what's our upper limit for that product?
0.
Yep, 0 is our lower limit for sure. Because 1/3 to the 0 is 1. Yeah. And our upper limit?
4.
Yeah, because 0, 1, 2, 3, 4, right? Exactly. All right, everybody, just take a second and write the other one. And are you worried about anything at all with this one? Does anybody see any potential issues? Anybody worried about 0 at all? Like, are you worried about -0? It's okay. It's okay for J equals 0. Why? Because what is negative 0 anyway? It's negative 1 times 0, and that, of course, is 0. So there's no problem. Okay? Questions? So this is the last of any of the material that you would see on test 2. I'm going to refrain from, pushing, forward further. So let's just think about the kind of the basic stuff that we really need to know in order to be able to do well on test 2. And I've kind of put together a list here. And then we'll look at some example problems. For sure, the definitions. All right, now remember, let's see, the very first definition we ever had was the definition of even, right? Back in the days when things were simple, right? Even and odd. And then we played prime and composite games. This composite definition is probably the most difficult, most challenging definition of all, right? It's got more parts than any of the other ones. Perfect squares we looked at, perfect cubes, rational number, divides, QR theorem, A mod D, A div D, course standard factored form. So we have 3 proof methods. Now listen, these proof methods apply to proving a universal statement, right? When we're just giving a counterexample or proving an existential statement, we just give an object X that fulfills the negation. That means X is in the correct domain and it fulfills the property of the negation, right? So, example proofs are, arguably easier because we can use specific values. But if we're trying to prove a universal statement like if P of X, then Q of X, the first method that we used for several weeks exclusively was direct proof. Assume P of X, we wish to show Q of X. We have that nice chart that was in the lecture notes. It's also in the good stuff folder called name of the proof method, and it's got a little chart. For proof by contrapositive, what do we assume, folks? What would be our hypothesis?
Not Q. If
Good.
not Q, then not P.
Yeah, so the hypothesis would be not Q, and we would wish to show not P. So I hope everybody understands. Listen, proof by contrapositive, it's just a direct proof of the contrapositive if then, right? But, it's obviously the better proof method for some of the statements. We've seen that. And then the last proof method that we just learned is proof by contradiction. So what do we assume when we are writing a proof by contradiction? What is the hypothesis? What do we assume?
The negation of the statement.
Exactly. Just the negation of the statement, whatever that is. And then what do we wish in a proof by contradiction? Just in most simplest form. I'm not saying specifics, but in general. It's always the same wish in proof by
That a
contradiction.
contradiction occurs.
Yeah, we wish to show a contradiction occurs, right? We were trying to get something bad, like 0 equals 1, or a number is both rational and irrational. Okay? And then, of course, be able to write the negation of a conditional, right? We know, listen, I think there's only like 1 or 2 people out of 75 that are still giving me an if or a then in the negation of an if then, and that is really good. So if you're one of those stragglers, the negation of an if then is not another if then. It's an existent statement with an and. P happened and Q did not follow. So be sure you know that. I think everybody in here does. And then the original and its contrapositive. So these are the two, you get, that you need to know, the negation and the contrapositive. So here are some example problems, and they look a lot like special homework problems. It's not an exhaustive list, right? But it's a pretty darn good start. Prove the sum of an even integer plus an odd integer is always odd. Believe it or not, that's not a proof by cases. You can just use the definition of even and odd, and it'll work out in one case. Prove the product of two rational numbers is always rational. So that's the definition of rational. Prove if true, give a counterexample if false. Maybe you haven't realized this, but prime and composite proofs sure do lend themselves to I'll say proofs, I mean problems involving prime and composite give us really nice fodder for counterexample kinds of issues. So for all numbers P and Q, if P is prime and Q is prime, and P is not equal to Q, so they're distinct, we've seen that before, then P raised to the Q plus 1, so this whole thing is in the exponent, is prime. So if it's true, prove it. If it's false, cook up a nice counterexample by giving two primes, P and Q, that are different from each other. Verify that they are primes by talking about their only divisors, and then verify that P to the Q plus 1 is not prime. In other words, this will be big enough that it'll have to be composite if it's not prime. Here's a proof by cases. It's very similar. The only difference here is it's negative 11 from the homework, and this factor of 3. It makes the algebra a tiny bit more interesting. So if n is in z, then n squared plus 3n minus 11 is odd. That's a proof by cases. What is the divisor there? How many cases will we have?
2.
Yep, because we're talking about even and odd. We're talking about something being odd. So we're dividing by 2, looking for a remainder of 1. Here's just a real straightforward divides problem. If A divides B and A divides C, then A cubed divides B cubed minus C cubed. Listen, if you just can look at that and realize I know exactly how to do that, you don't have to work all these. Here's some more. There's 10 of them. And again, the notes are posted. 6 is prove for all A, B, C, and D and Z that if AC does not divide 3BD, then A does not divide B or C does not divide D. You saw something similar, but not in this form in WebAssign. So attend these, these hypotheses, right? Of course, it's a does not divides problem. What's going to be the proof method for that?
Take the contrapositive of it.
Exactly. Write the contrapositive, and suddenly you'll have that A does divide B, and, because this will flip to an and, C does divide D as your hypothesis, and then you'll try to show that AC does divide 3BD. It's a cinch. Here's one more. This one's got the twist where it's not that A divides B and A divides C. It's going to be that A divides B and B does divide C when you take the contrapositive. So I wanted to give you one of each of those. Number 8, if A is rational, then A plus square root of 2 is irrational. You may assume square root of 2 is irrational. What's the proof method going to be for that?
Prove it by contradiction.
Yeah, we're going to assume that A is rational, and we'll also assume that A plus square root of 2 is rational. When you put those two facts together, it'll force square root of 2 to be rational, and that will contradict the fact that we can assume it's irrational. Go ahead and finish the do now from today if you need practice with algebra and cases. And here's one more A mod and B mod problem. I used mod 9. And, you may be more comfortable working number 10, and maybe even a couple of these others after you get some feedback from me on this last homework. Okay, because in this last homework you had the proof by cases. I need to grade that. In the last homework you had an A mod, out of what was it, 8, and a B mod 8 problem. Okay. So I am, so for the first time, you know, in our history, this fall, you know, class is officially dismissed, but I'm hanging out, and I am happy to go over any of these example problems with you. You know, if any of these, like I said, the notes are actually posted already. So, you know, if you want to open them up in a different window so that, you know, if you don't, but, or you can write them all down. So it's up to you. Any questions at all? I'm going to go back to the gallery so I can see everybody. You good? Believe it or not, even though it's a lot of proofs, I think you'll find that test 2 is a little easier than test 1. For one thing, you've already, you know, survived a test, right? And we've practiced these so much. You should be able to sit down and pin them off, you know. I hope so. Anybody want to work any of these? Just take your pick and we can attack. No. Tonight is Wednesday night. I'm going to sit in office hours from 8 to 9. I'll be there. And oh, God, I can't believe I got the computer working again with some help. Man, we had to crack that thing open and like repair the boot drive, and holy cow. It was kind of scary in there. Screws the wrong size, stuff rattling around in the tower. Anyhow, computer's working. So if anybody is around for office hours, that'll be recorded and the notes will be posted. I was able to recover files, so that was good. I know everybody in here knows, you know, the nightmare of your computer breaking down. I got really lucky. All right. Well, I'm just going to go in and stop recording, but I'll hang out, you know, a bit longer. If you change your mind and decide you want to look at one of these right now, if you want to pop back into office hours a little later, we can attack any of these or anything else. Otherwise, I'm just going to be sitting in there grading your homework. It's a busy week. Ever feel like you just bit off more than you could chew? Like the first week of class, you know? It's been like that ever since, right? Holy cow. What a life. I'm so happy to have gainful employment. Okay, I'm going to stop recording now.